Hi everyone and welcome to PrepFusion. I'm Anish and today we will be starting the lecture 5 of state space. So this will be a bit different lecture. Okay, this will not be the conventional lecture because in this lecture, right, what we will study is mainly mathematics. Okay, because we need a basic understanding of these terms before going into the next part of this chapter, right, for state space. So without understanding these terms we won't be able to study the next topics, right? So that's why we'll study this. Obviously in mathematics you will also study this, but here I will give you a brief idea of all these things. Okay, if you have any other doubts or anything, you can always post it in the doubt group of our Telegram channel, right? So I will go in a bit brief about eigenvectors and eigenvalues. What do you mean by eigenvectors and eigenvalues, right? So if you aren't able to catch up or not able to understand, then you either post your doubt in Telegram or you have to clear it out by watching the mathematics lecture. Okay, if that has been uploaded, if that has been completed by now. Okay, so yeah, the first thing is if you want a bit of more visualization, right, so there is a great channel known as 3 blue 1 brown. Okay, and you search there the title that eigenvectors and eigenvalues by 3 blue 1 brown. The channel name is 3 blue and 1 brown. Okay, you search this eigenvectors and eigenvalues by 3 blue 1 brown, and there you will see one visualization, right? 15 minutes video. If you want to see the whole, that's fine. If you don't want to, that's also fine, but see the video there. He has taught it really well, like the visualization of what we are actually doing using eigenvectors, right? What do we mean by matrices and what happens. Okay, so all those things you will understand by visualization. Here I don't have enough time to do all that, and he has done it very well, pretty well, so you can watch that video. Okay, so yeah, that was one information. Now what terms we have to know before learning about eigenvalues and eigenvectors. So terms to understand. So what do you need to know? The first one is transformation. What do we mean by transformation, and why we need to know transformation in the first place in this matrix matrix format, right? Why are we interested in transformation? And the next term is span. Like, what do we mean by span of a matrix? Okay, or what do you mean by span in general? Okay, so these terms generally in mathematics, right, are very confusing. Okay, you don't understand the meaning of all this. If in gate examination in engineering mathematics they give some question in span, you will be confused. Exactly. Okay, so we will understand the meaning of span. And third, what is rank? Okay, span and rank are basically similar only. We understand the similarities between span and rank. Okay, then okay, let me write this third a bit better. And fourth is basically what are linearly dependent and independent vectors. What do you mean by linear dependence and independence? Linearly independent vectors, right? And fifth is basically again coming back to the end stage, that is eigenvalues and eigenvector. After learning all about all these terms, then we'll understand what do we mean by eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Okay, so all these terms we'll learn, right? So now let's understand, like, what do we mean by transformation? Okay, what do we mean by transformation? But first let's understand how do we define a vector, right? So you have studied it from class 11th, I think. So let me write a vector. Okay, let's name that vector as v. Okay, and the bar represents that it has some direction associated with it, right? Not the bar, the arrow, right? It has some direction. Okay, so what I can write here, v arrow, v cap, or what do you say is, let's say 3 I cap plus 4 j cap. So I hope you understand what I cap and j cap means. Okay, so what does I cap and j cap means? Basically I cap is along like two axes, right? Along x axis is I cap and along y axis what is there, it is j cap. So if I draw two axes, right? Okay, this is my x, this is my y. Now along y is my j cap and along x is my I cap, right? Now what does this mean? That this means that I have to move, like I cap is the unit vector along the x direction. Okay, one step, basically unit means one step. So let me define this as one step only. Okay, this is 1, this is 2, this is 3. Okay, and this is also 1, this is also 2, and this is also 3. Okay, so all these let's say this is along unit vector along y, that is j, this is 1 j cap and this is 1 I cap. So what this is telling us is to move 3 steps along the x direction. Okay, then move 4 steps along the y direction. So my point, right, my point will be along here, but I have to find direction. So direction is respect to what? Direction is always respect to the origin. So the vector, right, vector will be defined like this. This is the vector v1 with respect to the origin, not v with respect to the origin, right? So this is the basic meaning of this vector v, which is represented in the axis, right? Now like what does this called, like I and j cap, what are these called? We have been studying this since 11th, right? So these are, right, these are called basis vector. Why? Because according to the base of this we are defining other vectors, right? These are our bases. Okay, and what are the fundamental properties of basis vector? You will study more. I will just give you a brief about basis vector here, that they will be orthogonal to each other or they will be perpendicular to each other, right? So why? I cannot represent this I cap with respect to this j cap. Okay, I cannot. Okay, this I and j are perpendicular to each other. I cannot represent this I cap by using j cap. Okay, and vice versa. I cannot represent this j cap by using this I cap. Okay, but I can represent this vector with the help of these two. Okay, any vector that is lying in this 2D plane, right, I can represent with the help of these basis vector. Okay, but what matrix helps us to do is transform the basis vector, right? So v, right, v can also be written in matrix format also. How? Okay, v can be written, and here is like 3, 4. Okay, v can be written like this also. Okay, in matrix format also. Now what does matrix format like helps us to do? It helps us to do the linear transformation of vectors. Okay, so basically if I want to do some linear transformation, right, so if I want to convert from one basis to another basis, okay, if I want to convert from one basis to another basis, then I will do linear transformation with the help of matrices. That helps, right? Matrices helps us compute it much faster. Okay, compute it much faster. Now you may ask why we want to change the basis, right? Why we want to change the basis? So let me give you an example. You are on an aeroplane, right? You are on an aeroplane. Okay, it's going straight like this, Now suddenly what happened? Let's say not you. Okay, you are in a war. Okay, and you are on a helicopter and it's going like this, jet plane. Now suddenly your jet plane has to move like this, right? Due to some reason. Okay, due to like give down a bomb or something or whatever. Okay, you want to move like this. Now, right, it has to decide. Now it's left and right are changed, right? Left and right are changed. But you have to move it like this. Okay, you have to go it like you have to go in this direction or this direction. But according to this, the direction has changed. The direction of left and right are changed. So but you have to go in this direction, right? So for this to go in this direction, it has to compute, right? It has to compute. Okay, that's why we want to change. Okay, our basis was this one, like this and this, but now our basis has changed to this. Okay, but I have to convert it to this one so that I can move in this direction, right? So matrix helps us to do all those things. Okay, matrix calculations. So I just gave you an example. If you couldn't understand, this is a practical example, okay, of the matrix calculations. If you couldn't understand, that's fine. You can always ask us in the Telegram group. Okay, I will not explain like the transformation further because this lecture will go very long. Okay, and that is not much of a significance to us. Okay, but if you want to have a practical knowledge, you can always check that channel. Okay, also if you can ask me doubt in the Telegram channel also. I won't make this lecture very long. Okay, so yeah, this was basically the thing about transformation. So transformation means we want to transform from one basis to another basis. So this is one basis, right? But I want to transform it like this basis. Okay, this is my this is like my x dash and this is my y dash. Now my vector is defined in this x dash and y dash, but I want to convert it into x and y, okay, according to this basis. So if my vector lies somewhere here according to this basis, but according to this basis where my locations will be, that I can do by matrix transformation, and from there I will understand. Okay, so yeah, that's what matrix helps us to do. Okay, and lot more other things also. So yeah, that was basically what transformation is. Okay, I will transform the basis vectors. Now let us understand what does span mean. Okay, what does span mean? Span, right? So let me again, now what I will do, I will take two vectors. Right? I will take two vectors. One, let me take here, one is v1 vector and another is v2 vector. Okay, one is v1 vector and another is v2 vector. Now this is I cap plus j cap. Let me take this just as an example, and this is I cap minus j cap. Okay, so I hope you understand the vectors already, like we have studied this since class 11. So yeah, this concept should not be left out. So this is x and this is y, right? Now where will this lie? This will lie like one step here and one step here, so this will lie somewhere around here, right? v1. Okay, and where will, okay, let me write this in different pen. Where will the v2 lie? V2 will lie, like it will go one step along this x direction, but it has to come down also, so it will lie here only. It will lie here only. Okay, so v2 will lie here only. Okay, so yeah, this is what my v1 and v2 will look like. Now what does span mean here? Span means with the combination, linear combination of v1 and v2, how much area can I cover? Okay, slowly I will take more examples, from there you will also understand. Okay, what do you mean by linear combination? So if I do linear combination a v1 plus b v2, this is the linear combination basically. How much area can I cover? Okay, how much area can I cover? So this is what span means. This is what span means. So can you tell me how much area can I cover? Like you have a basic idea, right? With a linear combination of these two vectors, okay, this one and this one, can I cover this whole plane, xy plane, or can I just cover one plane? Okay, or can I cover 3D planes also? Okay, this is 2D, right? This is 2D. So what can I cover? So yeah, I can cover only this whole plane, right? 2D plane. So the span will be 2D in this case. Why? If I put any two value, any values, right? Any values of a and b, like what I am doing is I am varying a and b, right? I am varying a and b. So I and j are varying, right? I and j can be any value. So this I and j can be covered by this whole 2D plane. Okay, so for any values of a and b, we can reach anywhere in the ij plane. We can reach anywhere in the ij plane. Okay, why? Because like a is fixed to here, then b is fixed to here, so I can change the a, right? I can change the a and b together to cover the entire xy plane. So can vary a b to cover the entire xy plane. Okay, entire xy plane. So this is what basically span means. Now let's take another example. Okay, let's take a third vector. Okay, example. Okay, let me take v3 equals to I plus 2j. Okay, I plus 2j. Now what will be the span of what will be the span of v1, v2 and v3. Okay, what will the span of v1, v2 and v3? So again, I will use the same formula. What area do I cover by the linear combination of v1, v2 and v3? So area covered v2, v3. So it will be simply linear combination, right? This is a v1 plus b v2 plus c v3, right? So again, what do I observe? What I observe is I can cover the entire Ij plane, right? I can cover the entire Ij plane. Why? Because with the help of this, anyways, I would have been able to cover the entire Ij plane. But this v3, right? This v3 is nothing but a linear combination of these two only, right? If you do a linear combination of v1 and v2, okay, v1 and v2, you will see that we are getting simply v3, right? So that's why again we'll cover the entire Ij plane. So v3 doesn't change anything, or v3 doesn't change the span if it is a linear combination of the previous two vectors, right? So entire Ij plane, y as v3 is a linear combination of v1 and v2. Okay, you calculate, you will find a linear combination between v1 and v2. Now why is this the case? Why is this the case? So let us do the proof, right? Let us do the proof. Okay, what about the proof? So I have this, right? A v1 plus b v2. Now this is c, right? v3. Now what I can write c v3 as, I can write v3 as some k1 times v1 plus k2 times v2. So this is the result of v3, right? I will get v3 in terms of v1 and v2, okay, as a linear combination. Okay, now I can rearrange this equation. So this will be a plus ck1 v1 plus b plus ck2 v2, right? So what I am saying is this is also a number constant, this is also constant number. So again I am getting the same thing again as the previous one. Okay, hence that's why if the new vector is linearly dependent, linear dependent, I hope you understand, the dependency is like this, it is dependent linearly, from constants with respect to the previous two vectors v1 and v2 linearly, right? So this is not non-linear, so this is linearly. Okay, so if the new vector is linearly dependent with the old vectors, then what is the key point here? Then span won't change. Okay, then the span won't change, it will remain same, it will remain same. Okay, it will remain same. So span will remain same. Now what happens if v3 is not linearly dependent, it is independent? Okay, what happens if v3 is in some other plane? what happens if v3 is in some other plane? Then what will happen? Then span will change. Then span will change. Okay, so v3, let me take let v3 equals to 5 k cap. Okay, v3 equals to 5 k cap. Now what will happen? Now our span will become whole 3D plane. Why? Because we have I and j combination up there, okay, on the previous v1 and v2, but we have new k also. So now span will become the whole 3D plane. Okay, I hope you are understanding, right? The previous v1 and v2 are a combination of I and j, and our new v3 is only k, right? So I have got all I, j and k together, so I can get the whole 3D plane, right? So here let me draw. This is, let's say this is I, this is j, okay, along the j direction. Now I have a new direction which is perpendicular to both I and j. This is the k direction, right? K cap. So I can get combination of both I, j, k everywhere at all the points. So whatever I get, I will get a volume. I will get a volume. So I will be able to cover the whole 3D plane. So span will become 3D right now. Okay. Span will become 3D. Okay. So like let me write this important point, that if the new vector is linearly independent from the other two vectors, from the previous vectors, then the span will change. Okay, then in it will increase basically, but still I will write, then the span will change, right? So this is what about the span. So basically this is about the span only. Now let us study about the rank. Okay, let us study about the rank. Now what is rank? Rank basically tells us about the span of the matrix. So it is similar to span only. Tells about the span of the matrix. How? Let me take an example. Okay, so I've already explained it to you. What does how do we find the span, right? With a linear combination of two vectors, can I cover the entire 2D plane or 3D plane, whatever? Okay, in this example also the span will get more clearer. Okay, so let me take an example. I have two vectors. One is v1 vector whose direction is like this, 1 I cap plus 2 j cap. I am writing it like a column vector, right? 1 I cap plus 2 j cap. Now I have another vector whose direction is like this, 2 I cap plus 4 j cap. So what is the interesting thing you observe about the directions of these two vectors? Okay, what is the interesting thing you observe? What? It is in the same direction, right? Both of the vectors are in the same direction, just v2 is more larger in length than the v1, right? So let me draw the vectors here. So the first vector, right, is we're going one unit in the I cap, and then 2 units in the j cap, so I will write somewhere around here, okay, somewhere around here. And for the other one, right, I'm going 4 units, 2 units on the I cap and 4 units on the j cap, so I will write somewhere around here, right, somewhere around here. So this is my V1, okay, and this is my V2. This is my V2, okay. So what I can see, like, obviously from here also I could understood, but here also I can understand that these are in the same direction. So yeah, let me write this here. This is 2j, this is I, this is 2I cap, and this is 4j cap, okay, this is 4j cap. So yeah, these are the x5. So this is basically V1 and V2, okay. So yeah, from here, can you tell me the span of V1 and V2, okay? Span of V1 and V2. So what will be the span this time? So how do you find the span? So this is a V1 plus b V2, right? A V1 plus b V2. Now can I expand the V2, right? So I can apply the same theorem that I told you just before, right? What? That if this, let's say this was the span, okay, initially I had only V1, okay, what will be the span of V1? Okay, the span of V1 will be 1D only, one direction, because I'm covering a line only, right? I'm not covering whole area, okay. I can only scale this, right? If a is multiplied, so a times 1 plus 2j, it will go like 2 plus 4j, 4 plus 8j, like that, okay. It will keep on increasing. I will go along this line, right? If I keep on changing a, okay, I have only one vector, right? Now if I have this new vector, but what I am saying is this is linearly dependent on the previous vector. How? 2 times this is V2 only, right? 2 times this is V2 only. So according to my previous point, right, key point, it won't change the span. It won't change the span, okay. So yeah, that is the important thing to keep in mind. But I will also like write this down here so that you can understand it better, man. So here, right, this is a V1. What is V1? Let me write like this. This is I plus 2j, right? I plus 2j plus b. What is this? 2I plus 4j, right? Now let me expand this. Okay, let me take common I plus 2j, right, from both of this. So if I take common I plus 2j, this is a plus 2b and this is I plus 2j, okay. So like if you take it common, I hope you know how to take it common, right? So if you take it common, what I am observing is like it is a scalar multiple of this I plus 2j. This is a particular direction, right? I plus 2j is a particular direction. What I am doing is just scaling this line. I can scale this like this, or I can go in the negative direction. I can go from here. I can go in the negative direction or this direction. I can only cover a line, right? I cannot cover the entire ij plane. In the previous example, if you expand that, right, ij, what you will see is that we can cover the entire plane. Like in the previous example, that was the 3D only. In the 2D example also here, right, what you can see, I can individually, right, change the values of j and I. How? Like let me expand this here, okay. So yeah, let me expand this here. So a v1 plus b v2, right? So this, right, this becomes I plus j plus b, this is cap, I minus j. So this becomes, right, a plus b into I and a minus b into j. So individually I and j can change, right? Individually I and j can change. So I can cover the entire 2D plane. I can cover the entire 2D. So this will be plus Okay, I can cover the entire 2D plane with respect to the combination of a plus b and a minus b. Okay, but in this case, right here, like with the combination of a and b, I can only scale this I plus 2j. This is constant. I plus 2j is constant. It is not changing. But there I and j both were changing. Okay, but here I and j are not changing. The direction is not changing. Just the scale is changing, right? Just the scale length of the vector is changing. Just the length of the vector is changing. Okay, so there the like the length was also changing, but the direction was also changing. So it was 2D. Now what will be this? This will be 1D, because this is just a line. So for line, you remember 1D. For point, it is like 0D only. Okay, there is no dimension for point. And for area, it is 2D. And for volume, it is 3D. So these are basic things. I hope you already know all this. So span will be one D only in this case. Line, okay, it's just a line. Okay, so span, right? I was explaining rank here. So what is like a rank? Rank is equivalent to span. Rank is equivalent to span basically. How? So I have this. Now what I will do, I will write this in matrix format. How? Like I know you have studied in college your matrix, basic matrix, I know that. Okay, so how I will write in matrix format? So in matrix, right, the two vectors v1 and v2, they are two column vectors. So the first one is 1 2 and the second one is 2 4. So I know you know how to calculate determinant. So the determinant comes up here 0, but we will not go that route. We will go that route a bit later in this lecture. First, right, what I see is this vector is a linear combination of this one. So 2 times this is this. So here, right, the rank of this matrix 2 cross 2 matrix, right, rank of this 2 cross 2 matrix will be 1. Okay, rank of this 2 cross 2 matrix will be 1. Okay, why? Because the span is only 1D, right? Span is 1D. We're only covering one direction, only one direction. Okay, from there you can also understand, from here you can also understand that this is a linear combination of this one. Okay, that's why the rank becomes 1. Okay, now right now what if they are in different direction? What if they are in different direction? So let's say now if v1 and v2 are in different direction, so what will happen basically? So let me take an example. So let's say I have this 2 3 and this is in, let's say, -1 4. Okay, so I won't be able to write linear combination of this one with respect to this. This is not a multiple of this. So what will be the span this time? You again follow the same process. You will find that span is 2D, right? I can cover the entire xy plane. So what will be the rank? Rank will be 2 only. Okay, rank will be 2 only because the span is 2D. I can cover the entire xy plane. So that's what basically like a rank signifies. Also rank, right, rank can be calculated with the help of determinant. Okay, I hope you know already determinant. So for 2D, right, for 2D, what does determinant signify? For 2D, determinant signifies area, right? So if the area is 0, then definitely the rank will be less than 2. Rank will be less than 2. It can be either 0 or 1. When can it be 0? Just think, when can it be 0? When this is a null matrix, right? So then rank will be 0. When can it be 1? When this is a like linear combination of this one, right, or multiple of this one. So that's how rank can be calculated using determinant also. Now for 3 cross 3 matrix, right, what you can say is like it is like determinant. What does it signify? It signifies volume. Okay, signifies volume. So but you might say that I am getting negative sometimes, so it is in the bottom half, that's why you are getting negative. So don't take it like how can volume be negative, because it's in the negative direction, that's why you're getting the volume as negative. But that doesn't mean anything. Just the main thing is determinant for 3 cross 3 matrix signifies volume, and for 2 cross 2 matrix it signifies area. Okay, these things you understand a bit. Okay, so yeah, that's how this is basically it. Now if you calculate the determinant of this one, what you will get is 0, right? As this is a linear combination of this one. Okay, you will get 0. 1 times 4 minus 4, that is 0 only. But if you calculate the determinant of this one, this is 2 times 8 plus 3, that is 11 only, right? That is 11 only. So yeah, you see this determinant is non-zero and this is 0. So here the area is 0. Definitely the rank can't be 2. It will be something less than 2, because I am not covering any area, right? I am not covering any area. Okay, and here I am covering some area, so definitely it covers the span, it covers the 2D span. Okay, so yeah, that was for basically a determinant and span. Okay, so let me write this down here. Okay, so all these things, right, these are explained in very brief manner. So you, if you understand, that's well and good. If you don't, you can like ask in Telegram group on the doubt group, or like you can study by yourself, or from the maths lectures, right? You can study from there also. So because this is not for we don't need too much of knowledge about this in control system, but the conclusions are very important from what we get, right? From what I am trying to get at. So but before understanding the for us to understand the conclusions, we have to understand all this. That's why I'm teaching you this. Determinant equal to 0, right? Means span will definitely not be 2. Something span will be less than 2. I can say less than 2. Now if determinant is not equals to 0, then that means the vectors are independent of each other and span will be 2. And the vectors are like, I hope you understand what does linearly independent mean now. So either it is not a linear combination A and B, combination of two vectors if I have two vectors, but since I have only one vectors, so it is not a times v1, v2 is not equals to a times v1. So now we can say it is just not a multiple, scaling multiple of v1 v2, right? So that is what you can call. Okay, but for one vector. But if you have two vectors, v1 and v2, so v3 should not be a linear combination of v1 and v2, that is a v1 plus b v2. We cannot write v3 from that linear combination, so then they will be linearly independent. Each other. So yeah, this is basically the basic crux of rank, span, linear dependence, independence, and basically the what do you call, the transformation, right? So all this I went through very fast just to give you a brief idea. Okay, just to give you a brief idea. So now let's do a few questions. From there your concepts will get more clearer. Okay, so this is the, I think, the 7th question. Okay, 7th question. So these are the theoretical questions. Okay, very quick, but if you understand the concept, then only you will be able to solve this. This is not a mathematical question. So let's say I have two vectors, k1 and k2, right? K1 and k2. Okay, now I have another third vector. Third vector is basically a cross product of k1 and k2. k1 cross of k2. Now what I want to know is what, like, and also k3, the result, right? K3, the result we get after cross product is a non-zero vector. I don't know about the direction, but k3 is a non-zero vector. Okay, k3 is a non-zero vector. Okay, and just remember this k1 and k2 are all written in terms of I and j. So like the rank of these two are 2 only, right? 2 I and j. Okay, not rank, but they are written in terms of I and j only. In terms of I and j only. K1 and k2. Okay, now k3 I get k1 cross k2. Now what you have to find is find the rank of k1 k2 k3 k1 k2 k3. Okay, k1 k2 k3. So that is what is important. So basically, right, just think what can be the rank of k1 k2 k3. Will it be 2? Will it be 1? Will it become 1 as it is dependent on k2 k1 k2, or will it be 2 only? Because yeah, if it is dependent, the rank won't change, it will remain same, right? K1 k2. Just think what will be the rank of this k1 k2 k3. So what I know from my class 11 days is that if I do a cross multiplication, right, the output direction that I get of k3, right, it will be perpendicular to k1 and k2. Okay, so it will be some other direction, right? Some other direction. So let's say if this k1 is I cap and k2 is j cap. So let's always try some simple example. This is I cap and j cap. So what will k3 be? It will be k cap, right? K cap. Now if this k3 is k cap, then what will happen? Then I am getting a new direction which is linearly independent of k2 and k3. So what will be the rank now? So rank will increase, right? So as these three are linearly independent, I cannot write these as a linear combination of these two. Okay, because k cap is itself in some other direction. Okay, k cap is itself in some other direction. Okay, so yeah, from cross product direction orthogonal, or you can say perpendicular. Orthogonal to k1 and k2 with the help of cross product. That's why hence rank will be 1. Okay, sorry, rank will be 3. Rank will increase because all three are linearly independent. Okay, as k1 k2 k3 are linearly independent, right? So this is what basically the first question tells us. Now let's do another question. Okay, let me name this as the 8th question. Okay, so if right now k1 cross k2 is equals to 0. Okay, so I am giving you this result by myself. K1 cross k2 is 0. Also k2 cross k3 is 0, right? Now tell me that also one more information is there, that k1 k2 and k3 are by themselves, they are non-zero, right? They are not zero. k1 k2 k3 by themselves are non-zero. So what will be the rank of k1 k2 k3. So rank what will be the rank of k1 k2 k3? So rank, right? So what will be rank? So what I can see, if cross product of two vectors are 0, what does that mean? So what was the result of cross product? Just remember, the result of cross product was mod of k1 mod of k2 times angle between them, sine of angle between them. So if each of them k1 k2 are not 0, okay, so mod of k1 k2 are not 0, then what will happen? Then the sine of angle of between them should be 0. What does mean? They don't have any angle. Sine 0 is 0 only. So that means k1 and k2 are in same direction. So this means k1 and k2 are in same direction, okay, and this also means the same thing, right? This also means the same thing. K2 and K3 are in same direction, okay. K2 and K3 are in same direction. So if these two are in same direction, so what will the meaning of this? That means this K1 and K3 are also in same direction. So is that the case? So if all three of them are in the same direction, so we can write combination of one as the other one, right? So only one vector is linearly independent and other two vectors are dependent on other. So only one vector is linearly independent and other two vectors are, okay, let me write this in better manner. On it, okay. So this is just like the example where we had only one line, right, and the other vector was in the direction. So here what will happen, instead of one line, instead of two lines, we have three lines and three of them are in same direction. So what will be the span will be one only, right? One only. Why? Because simply they are in the same direction, so I can scale it in this direction only. I cannot cover the entire xy plane or the ij plane, right? I can only scale in this direction. So yeah, that's why this will be like this one only, this will be like this one only. So yeah, so the rank of this one will be 1 only. K1 K2 K3 will be 1, okay. Also you can say that the three vectors are collinear, okay, or parallel with each other. Okay, so three vectors are collinear or parallel with each other, okay. So this was the important thing to know, okay. So yeah, these are the questions. So now we will understand what is an eigenvector. So before studying the eigenvectors and eigenvalues, we have to learn all those terms, right? So now we will come to our main topic basically. So I will write here eigenvector, okay. So what is an eigenvector basically? So let me explain it to you. Basically, right, if I have a matrix and I apply some transformation, right, multiply with the vector, okay, and what do I get? I get the same vector in the same direction. I get the same vector in the same direction, but a scaled version of it. So let's say I have a graph, right? I have a graph, okay, and I have this vector, let's say v, okay, v vector. Now I have multiply this A matrix. I do A times v, right? A times v. What happens is that I get the same vector in the same direction, okay, same direction, okay. What do you mean by same direction? Like this. But what is difference? It is just a scaled version of this vector. So this will be some lambda times v, right? Lambda times v. So this is a scaled version of this vector, right? So this is what basically eigenvector is. So eigenvector is this v vector, right? Is this v vector in which if I multiply some matrix A, okay, then I will get the same scaled version of this vector in the same direction, right? In the same direction, scale version of this vector in the same direction, or it can be like this also. Then it's just minus, okay, it's just minus, but in the same line, right? In the same plane, okay. The direction is same, it's just in the negative direction, okay. So yeah, that is what a eigenvector is. That is what a eigenvector is. So after applying some transformation to A, I get the same direction, right? But it's just a scaled version. So let's, for example, now eigenvector of what? Eigenvector of A, okay, the matrix A. So let's take an example. I have A, right? I have A matrix. Let me take the numbers as 2 0 and 1 3, okay, 2 0 and 1 3. Now after taking the transformation, okay, after taking the transformation, we'll get the same direction. So what should I write the equation as? Equation, what should I write here is, this is A and this is a vector v equals to lambda times v, right? So the result of this will be same, will be in the same direction. So v vector, right, will be a eigenvector of this A matrix. That's how we call it. So v vector will be a eigenvector of this A matrix, okay. So let me write here, v vector will be eigenvector of A, okay. V vector will be eigenvector of A, okay. So it is that vector that doesn't transform the direction of the matrix, right? It doesn't transform the direction of the matrix, it just scales it. Okay, the direction remains same, okay. So let me write here also another definition. Matrix that doesn't transform the direction of A, okay. It just scales the matrix, okay. So yeah, this is the basically known as the eigenvector. Now what does eigenvalue mean? So eigenvalue is basically the scaling factor. This lambda, right, this lambda is known as the eigenvalue of this matrix. So eigenvalue is the factor by which it scales, okay, by which it scales. Right here, by which it scales the vector, right? Scales the vector. Okay, so this is what eigenvalue is, or you can say how much it stretches, okay. It stretches or compresses, like this vector, right? This vector is either stretched, like increased or decreased or compressed, okay. It can be less than 1 also, right? So yeah, that is what basically vector is. Sorry, eigenvalue is, okay. So yeah, let me write the equation here again. This is matrix A, right, and we're multiplying some vector v this is equals to lambda times v. So what is this? Basically this is the eigenvalue, and this is the eigenvector. Okay, so both of these things we have to find out. Now how I will say, I will tell you. Okay, so like another definition what we can say is this vector v, right, doesn't leave its span, it's in the same span, just as I explained, right? So it's in, like, if it's in this direction, it's in this direction only. The vector v doesn't leave its span. If we had have found out any other angle, right, then obviously it left its span and we can cover the whole 2D plane, but it is in the same span. So what I can say here is the vector v is in the same span. The vector v is in the same span. Okay, so yeah, this is what basically, as I explained. So here how to solve this equation, so like what equation we have, this one, right? So let me copy this. So I have to find lambda and v vector both for this particular A matrix, right? So why am I so interested in finding the lambda? This is known as the lambda, and the v vector for this particular A matrix we will understand while studying. So basically this lambda, right, this tells us about the poles of the system, right? And by poles we can know the behavior of the system, okay, and the stability, and find the stability of the system. All these things we will learn when we find study next few chapters, right? But that's why we are very interested in finding the eigenvalues and the eigenvectors. Okay, eigenvectors also we are interested because to study in the state space, right? So yeah, so what I will write here is, this is the A vector. Now we have the v minus lambda v, okay, equals to 0. Now what is 0? This 0 is the simply null matrix, right? Not simple 0, this is the null matrix. So I should write here as null matrix. Okay, and null, you can understand, right? You can understand this is a null matrix. This is not simply just a 0. Okay, so what I can do is take v vector common A. That is not an issue, right? Like matrix follows a rule of associativity, so it shouldn't be an issue. Okay, so I will take common v. Okay, now, right, this lambda I cannot just subtract like this with A. This will be lambda I. Okay, this will be lambda I. Why? Because this is a matrix. Now this has to be also matrix, right? If this is, let's say, if this is the unit of this is speed, right, then we have to subtract some similar amount, right? So like similar what do you say, unit, right? So this has to be also speed. For example, just example, if I am subtracting something like speed, so they have to be homogeneous. So this lambda, right, this lambda has to be converted into matrix form of I. Now one more thing, like this A, right, this A has, let's say this A is a square matrix, right? So eigenvectors and eigenvalues are defined for square matrix. Okay, so I am not going to too much details. I just need to prove some things to you. That's why I am going here. In mathematics class we'll go in the full details, right? So this is n cross n. Okay, n cross n, and which is like this, the order is n cross n, right? So I, right, identity will has to be also order of n cross n. Okay, just to subtract the similar amounts. Okay, so I hope you have already done this in college, so I'm not going too much into details. So this is n cross n. Okay, and this is also n cross n. Okay, and in the outside what do you have? We have v vector, which is equals to null vector only, right? Now I have to solve for this one, right? I have to solve for this one. When this is 0, right, then I can get a null vector. Or what is another possibility? When this v vector itself is 0. So a null vector, right, is a eigenvector of all the matrices. Okay, always. So if I multiply with 0, I get a null vector itself. If I multiply with null vector here, I will get a null vector as a equation. So it is always a solution. Null vector is always a solution, but I am not interested in null vector because that doesn't give me any information. Okay, so I am interested about equating this to 0. So how I will equate this to 0? For that I need to take help of the Cramer's rule. Okay, so in 12th I think we have already studied Cramer's rule, 11th or 12th. So just I will give you a brief overview of the Cramer's rule, right? Cramer's rule. So how do we like use the Cramer's rule? Let me first write a bit of theory. So Cramer's rule, right? For using the Cramer's rule, let's say I have a 3x3 matrix, right? 3x3 matrix. A1, B1, C1, A2, B2, C2, A3, B3, C3, and what is this? This is X, Y, Z, and this is D1, D2, and D3. Okay, D1, D2, and D3. Okay, so I have this equation, basically matrix equation, and I have to find the value of X, Y, and Z. How we used to do it? So what was X equals to? X equals to, if you remember it correctly, delta 1 by delta, Y equals to delta 2 by delta, and Z equals to delta 3 by delta. Okay, Z equals to delta 3 by delta. So this is what X, Y, and Z are equals to. Okay, so basically, right, now what is delta 1, delta 2, and delta 3? So if you remember, still I will write it. What is delta? Delta is simply the determinant of this matrix, right? Determinant of this matrix. So I will copy this. Simply determinant of this matrix. Now what was delta 1? So delta 1, right? For delta 1, I am getting the value of X. So what I will do is I will simply replace this first column with the like the right hand side, right, with the RHS. So what I will do, I will again copy and paste this, but I will replace the first column with the right hand side. So right hand side was D1, D2, and D3. Okay, this will be my delta 1. Okay, now what is my delta 2? So my delta 2, right? So delta 2, basically, again like using the same property, I will again cross this middle column, and I will replace this with the this D column, right? So what I will do, again I will copy and paste, so it's easy for me, but if you are writing, you have to write it totally. So replace this middle column, right, second column, basically, with the right hand side column vector. And again for delta 3, I'm just revising you this rule, right, Cramer's rule. Again the same thing we will do, but this time the third column, right? Third column. Okay, so this is the basically Cramer's rule when the right hand side is non-zero. Right hand side is non-zero, but in our case, right, what is easier is this right hand side is 0, so I will put the right hand side is as 0. Okay, so I will again copy this and make the right hand side as 0. Then what will be the case? This will be simply 0. Okay, then what will happen is that our delta 1 equals to delta 2 equals to delta 3 will always be 0, because one column will like except delta, one column will always be full of zeros, right? So our determinant will become 0. Now what we have to understand is we have at least one solution, just like the previous this case, right? That vector v itself is a null matrix. So here also we have always one solution, that is x equals to y equals to 0. If x equals to y equals to z equals to 0, then like at least we have one solution for any values of all this, right? If all of these three are become 0, then we always have a solution. So like x equals to y equals to z equals 0, always a solution, right? Always a solution. So this is one solution. Now, right, so if delta 1, delta 2, delta 2, 3 is always 0. Now delta isn't 0, right? Delta isn't 0. So like if delta isn't 0, delta is non-zero, and delta 1, delta 2, delta 3 is 0, then like we get x equals to delta 1 by non-zero, so it is 0, and this is 0, this is also 0, right? So that was solution that I was mentioning about. Now what is the interesting fact is that if delta also becomes 0, this becomes 0 by 0 format, this becomes 0 by 0 format. And what happens if the numerator and denominator are 0? We apply limits, right? We apply limits. So it is not like infinity or something, so we apply limit if we are getting 0 by 0 format. Okay, now if we are getting 0 by 0 format, so for that, like we'll get some finite value of x, right? We'll get some finite value of x. I hope you remember, if I get some 0 by 0 format, so what I have to do is, I'm not interested in the solution x equals to y equals to z equals to 0. I'm interested in the other solutions. Okay, in the other solution that gives me finite values of x, y and z, right? X, y and z. So I have to make this determinant 0. This determinant I have to make 0. Okay, so that is what is the mean factor is. That is what we have to do here also, right? We have to do here also. I have to make the determinant of this as 0. This is a column vector, right? This is a column vector, just like here, column vector, and I'm getting 0, right? Now this is my matrix a1 b1 c1 equals to this matrix only. Okay, I will write this down for you for a 2 cross 2. I will write this down. There you will understand it in a better manner. Okay, so I have to make the determinant of this 0 so that I find solutions for this lambda. So basically what this lambda is, right? Now, like what was the significance of eigenvector? I told you, right? I told you it is a scaling factor, but we have to find lambda this time. We have to find lambda. Instead of, we already know lambda or eigenvector, instead we know already the eigenvector, and from knowing the eigenvector, what we do is like multiply with it the vector, multiply with a, and then we find the scaling factor. But here we are going the opposite direction. What we are doing is, eigenvector we don't know, okay, so I take eigenvector common as here. Okay, I don't know the solution. What I will do, I will vary this lambda. I will keep on varying this lambda for the cases where this determinant becomes 0, but then after finding the value of lambda, from there I will find the value of eigenvector. That is basically my procedure. Okay, so here I will write this equation again, and I will expand this, right? I will expand this for 2 cross 2. Like for smaller matrices you will understand it better. So here I have a minus lambda I, and this is a1 b1 c1. So this determinant have to make it 0, okay, for me to get finite solution of x, y and z, like non-zero solutions. Basically for me to get non-trivial or non-zero solutions of x, y and z, I have to make that determinant as 0, delta as 0. Okay, not finite, but non-zero solution, because if like the determinant is finite, then 0 by finite we get 0 only. Okay, so I don't want that. I want something else, some non-zero solution. So let me write here only, for non-zero solution, what I do is make delta equals to 0. So here what I will do, I will expand this for 2 cross 2 matrix, n equals to 2. So let's say what a matrix is, A is simply 2 cross 2, right? So it is A, B, C and D. And what is I? N cross 1, it is 1 0 0 1, right? 1 0 0 1. Okay, 1 0 0 1. So now I will expand this. Basically this will become a minus 1. Okay, sorry, not 1, this is lambda times also, so lambda is outside here also, so lambda will get multiplied through the all the elements. So this is a minus lambda. Okay, and this is b only, b minus 0, this is c minus 0, and this is d minus lambda. Okay, d minus lambda, so this is my vector. Now what is this equivalent to here? Basically, right, this is equivalent to this a1 b1 a2 b2, right? So I have to make the delta of this 0, that is I have to make the delta of this 0. So the determinant, so I have expanded this, I will not write this again. Determinant of A minus, I will not write the this orders and all those things. All these are understood by you, right? For cleaner look of my notes, I will not write all this. I hope all this you know, like yeah, this is order of n cross n, this I is order of n cross n, lambda is just a number scaling factor, all this is in your mind, okay? I will not write this repeatedly, okay? So A minus lambda I determinant should be equal to 0, okay? So that is the main thing, right? That is the main thing for us to find the value of lambda. So what we do, I will keep on varying lambda, and for one such lambda or multiple values of lambda, I will get the determinant equals to 0 of this equation, okay? Of this equation. So that is what basically I will do. Now one more thing, how many values of lambda I can get? At max I can get two values, right? Two values of lambda, for which in this case when n equals to 2, so maximum values of lambda will be 2, right? I mean distinct value of lambda will be 2, right? We can get same values of lambda, but for maximum distinct number of values of lambda will get 2, that will be equals to the order of the matrix. All these properties I will write in the notes in the next few slides, right? So for now, that is this equation. Now this equation has multiple names, right? This equation has multiple names. So generally what happens is people just write this directly, okay? I have explained it to you why do you take determinant, all those things I have explained it to you. So this equation, right, this equation is also known as the characteristics equation. Why? Because with the help of this equation I can find the eigenvalues and eigenvector. Also with the help of this equation I can find the poles of the system, and like the denominator of the transfer function, right, is this equation only, okay? So yeah, when we study the control system like more in depth, there we will understand. So this is known as the characteristics equation. Now let us take the example, right? The same example, okay? Let me check what question we did, question number, let me check. This was the 8th question, right? Now let me take the 9th question. 9th question basically. So what is the 9th question? If I have a matrix A which is equals to 2 1 0 3, okay, 2 1 0 3, so what will be, find the eigenvalues, find the eigenvalues of this matrix, okay? So what I will do, again solve the characteristics equation. So equals to 0, A minus lambda I should be equals to 0, okay? So what is my A this time? So A, right, A is 2 0 1 3, and lambda is simply lambda 0 0 lambda is equals to 0, okay, is equals to 0. So again this will become 2 minus lambda, okay, this will become 0, this will become 0 again, I think, no, this will become 1 only, and this will become 3 minus lambda, which is equals to 0, So let's solve this determinant. So this is just like cakewalk for us. So this is 2 minus lambda into 3 minus lambda minus 0, so which is equals to 0 itself. Now we get two values of lambda, two distinct values of lambda. So lambda equals to 2, 3. So the eigenvectors that we get will stretch this by two values. One eigenvector will stretch this by 2 and another will stretch this by 3. Now how do I know that the eigenvectors, right, they will be different. Now think one second, the same eigenvector, if you multiply with a matrix, can it stretch at the same time 2 and 3 simultaneously? Can it do that? No. If a single eigenvector is multiplied with a matrix A, right, to transform it, I can only stretch it to one single value, right? I cannot stretch it to two values at the same time. If some eigenvector is stretching that matrix to the same in the same direction of the vector to 2, then I can't stretch it to 3. I need another eigenvector that will stretch it to 3. Okay, so we'll have two different eigenvectors. Okay, so the point to note here is, if I have two distinct eigenvalues, then eigenvectors will also be distinct. Now what if I apply the reverse rule? Okay, what if I tell vice versa? Is the vice versa true, that if I have distinct eigenvectors, will the eigenvalues be distinct? Just think, right? Think and tell me. If I have distinct eigenvectors, I have two different eigenvectors. Now I multiply with a matrix and I get the same eigenvector and some scaling factor, right? So will I for sure get different scaling factors? Now what is your answer? If your answer is they will be different, then it is wrong. Why? Because if I multiply like a eigenvector with a matrix to transform it, then it may so happen I will get the same eigen like same scaling factor, right? Same scaling factor. So if I multiply some eigenvector with A, I may get scaling factor is 2, and if I multiply a different eigenvector with A, then also I may get the scaling factor is 2. There is no fixed rule that no, if I get scaling factor 2 for this eigenvector, I won't be able to get scaling factor 2 for the other eigenvector. That is possible, right? That is possible. Okay, but if I have distinct eigenvector, that is not possible. Why? Because if I have distinct eigenvector, then like I will get different eigenvectors, because if I multiply a eigenvector with A, right, with A, then it's impossible for me to get two different scaling factors at the same time, right? Same time. But if I have a single eigenvector, if I have two eigenvectors and I multiply two different like eigenvectors with A itself, then scaling factor may be same. It may be same. Okay, just here, right, I have this direction and this direction, right? Now it may so happen the scaling factor here is also 2 and scaling factor here is also 2. Okay, so yeah, that is the main thing. Okay, so like scaling factor may be same, but the opposite is not true. That is basically if I have distinct eigenvalues, I will get different eigenvectors. But if I have different eigenvectors, it's not necessarily true that I will have distinct eigenvalues. Yeah, did I speak it correctly? So let me write it, then you will understand. Okay, but if I have distinct eigenvector, then it is not necessary that eigenvalues will also be distinct. Okay, they can be same, they can be different. There is no like a fixed rule, right? There is no fixed rule. Okay, so this was the point that I want to tell you about, right? So that is what the main thing is. So like what I am doing here, let me revise you that basically the main thing that I am doing, right? Firstly, I taught you the Cramer's rule for finding this equation. Okay, how to equate this, right? So finding the eigenvector is difficult. Finding the eigenvector is difficult for this matrix. So what I will do, I will find the eigenvalues. Okay, what I will do, I will like vary the lambda, keep on sweeping the value of lambda. Okay, and I will try to find the null space for one such value of lambda when this equation satisfies, right, and I get the null space, I get null vector here, like null matrix in this equation. But finding that is difficult. So what I do, first I explain it to you the Kramer's rule. Okay, and Kramer's rule we only need when this is 0. From there I understand that x equals to y equals to 0 is always a solution. Okay, why? Because delta 1, delta 2, delta 3 will always be 0. But I am interested in the other solution, because this, right, this is simply the null vector. I'm not interested in this solution, I'm interested in the other solution. So for the other solution, what I will do, I have to make this determinant as 0, so that I get here 0 by 0 format. So I will get some finite value. If this is 0 by finite format, so I will get some 0 value. 0 by finite is 0 only, but here I will get 0 by 0 format, so I will get some, not finite, so finite I will get definitely, but some non-zero value. It may come 0 also, it may come 0 also, don't get me wrong, it may come 0 also, but I will get some finite value. Okay, and I will get some most of the times some non-zero value. I'm interested in finding the lambda, right? So lambda is hidden in this equation and not here, right? So yeah, that's why I took that approach. Okay, so for that to be 0, so I have to make this determinant 0. That's why hence I expanded here that determinant needs to be 0. So if this determinant is 0, then I will keep on varying this lambda, and I will find the values of this equation when this determinant is 0. And here I have solved one question, and from there we understand that yeah, I will get two values of lambda. Now the things to note here is, if lambda that eigenvalues are distinct, then eigenvector will definitely be distinct. But if eigenvector is distinct, it is not necessary that eigenvalues will be also distinct. I drawn one graph, okay, and there I explained like this may scale it by 2 and this also may scale it by 2, no issues, they are in different directions, no issues. But if I have a single eigenvector, right, and I multiply, this can only scale it once, right? I can't scale it by 2 and then again scale it by 3. That is not possible in the same direction. That is not possible. Okay, so that's why the statement that I wrote. Okay, so now how to find the eigenvector? So I got the eigenvalues. I will put the values here, right? I will put the values in this equation. Yeah, where did I go? In the first primary equation. Okay, so let me say how to find the so put the values of eigen put the values of basically this eigenvalues, right? Eigenvalues. Okay, put the eigenvalues because the English will be wrong. In the scaling equation, right? Scaling equation. Okay, so like I will solve it, there you will understand. So what equation I had this equation, right? So this was the a times v. Okay, let me a times v equals to lambda times v. Okay, so we have now I will put this value of lambda in this equation, and I will solve for this. How? I will explain. So I will have two, right? Two values. So equals to, this will be v1. Okay, what will be v1? The eigenvector corresponding to lambda 1, value lambda 1, and what will be v2? The eigenvector corresponding to lambda 2, right? Okay, so this will be my v1 and v2. K will be two different eigenvectors as already explained. Okay, so let me solve the example here. Okay, here let me write also find the eigenvectors. Also find the eigenvectors, right? So let's find the eigenvector corresponding to eigenvalue equals to 2. So when delta equals to, or like lambda 1 equals to 2, then what will my equation look like? This will be a v1 times lambda 1 v1, right? So where v1 equals to x y, v1 equals to xy. Okay, so what is this basically equals to? So this, right? So this is simply, what is a equals to? A was equals to this one, right? 2013. So this is 2013. Okay, and v1 I should write as x1 and y1. So I will find the relation between x1 and y1. From there I will get my eigenvector. So this is 2013, this is x1 y1 equals to, what is lambda 1? Lambda 1, right, is equals to 2. Lambda 1 is equals to 2. And what is this vector? This is x1 y1. Okay, x1 y1. So now what will happen? So basically I will find the relations, right? So 2 times x1, I hope you know matrix multiplication. So 2 times x1 plus 0 times y1, so that is 0 only, equals to 2 times x1. So from here, right, this equation is always satisfying. This equation is always satisfying. So x can be any value. Okay, here x can be any value. Why? Because this equation is always satisfying. x1 can take any value. For any value of x1, you put x1 equals 0, you put x1 equals minus 1, this equation always satisfies. So x1 can take any value. That's why I wrote it like this. That's why I wrote it like this, right? Now in the next equation, right, in this equation, let's do in the bottom row, right? Equate the bottom row. So this is x1 plus 3y1 equals to 2y1. So what do I get from here? x1 equals to, let me write here is minus y1. So as x1 can take any value, y1 also can take any value, but one relation you have to follow is x1 should always be negative of y1, or vice versa, y1 should always be negative of x1. So in this case, what will be my eigenvector? As x1 and y1 can take any value, but they have to follow one particular relation. So how will I write my eigenvector? So what I will do is v1, right? v1 will be equals to simply 1 minus 1 times c. Okay, now what is the c? C can be any real number. C can be any real number. Okay, so if c is any real number, then if I multiply with the scaling factor, then this always follow the relation, right? That x1 is opposite of y1. If this is negative, then this will be minus and this will be plus. Okay, but for simplicity, I will take one value, right? I will take c equals to 1. Okay, so this eigenvector, right, can be like multiple values, but they have to follow this particular relation, and the scaling factor will remain same. For this. But obviously this is in some particular direction, right? This eigenvector is in some particular direction, right? This is in some particular direction. Okay, that is the main thing. This is in the same direction. It's not like it is spanning around other direction, right? So this direction is fixed. 1 minus 1 is fixed, and it is just scaling, right? It is just scaling. So if I just scale and multiply with this eigenvector, then I will get my desired, like this like the desired equation, this equation. Okay, this equation. So that thing is important. So what does this represent? This is a scaled in the same direction of 1 comma minus 1. That I hope you understand. So I hope you watch the 3 blue 1 brown video. From there also you will get the visualization of what do I mean by scaling in the same direction. Okay, so now let us solve for the v2, but first, for simplicity, c equals to 1. Okay, c equals to 1. So v1 equals to 1 minus 1. Okay, 1 minus 1. So what is this? So we get my v1. So now I will find the eigenvector v2, right, for like the eigenvalue 3. Okay, so equals to 3. So again I will write the same equation like this one. A v2 equals to lambda 2v2, and this time my v2, right, v2 will be equals to x2 y2. v2 will be equals to x2 y2. Okay, so what will be this value? So again I will expand. A is 2103, v2 is x2 y2, lambda 2 is 3 this time, and this is also x2 y2. Okay, so again I will solve the equations. So this is again 2x2 equals to 3x2. Okay, so now can x2 take any value? No. Why? Because if I cancel x2 here, then 2 equals to 3, then the equation becomes invalid. Then what is the problem? Let me cancel the x2 because we can take common, right? So 2 equals to 3. Okay, what is the issue here? Is 2 equals to 3. So the problem is I simply cannot cancel this. Why? Because I haven't considered for the case when x2 is 0. So if x2 is 0, I simply cancel. I can't simply cancel this, right? I can't simply cancel this. Okay, so what I have to do, how I have to solve in this case is simply bring this over to this side or this side, whatever you want to say. Okay, I will bring 3x2 minus 2x2 equals to 0, right? I can't simply cancel x2 because x2 can be 0 as well, and I can't divide on both sides by 0. By cancelling, what do we do? I divide by both sides by the same number, right? Okay, but I can't divide by 0. That's why I can't cancel. I can take it to one side. Then what I can do is, like, what is 3x2 minus 2x1? x2 is x2 itself, which is equals to 0. So from here I get a solution. Okay, just be careful when we simply cancel, right? So we divide by the same number, but I can't do it here. So yeah, this is what my x2 is equals to. So x2 is equals to 0. So x2 can't take any value. Okay, then what will be my y in this case? So y, right? Solving the second equation. So this is x2 plus 3y2 equals to 3y2 itself, right? 3y2 itself. So again this is this is simply cancelling it out. Okay, let me check here. This is 3y2. Yeah, so here, right, what is happening is y2 can take again any value. y2 can take again any value, because for any value of y2, right, this equation is always satisfied because x2 is 0. So again, like, how I can write this as 3y2 equals to 3y2. So for any value of y2, this equation will always satisfy. Okay, so okay, so what I can write here is simply y2 is any value. So how will I write my vector v2 this time? So I will write c times, like, let me name this as c2 because that previous one was c1. So so I will write here is c1. Okay, c1, this is c2. And what is this vector? This is 0 because c2 times 0 is 0 only. So x2 has fixed value, that is 0 only. But y, right, y can take any value. So this is 1. Okay, so again c2 can be any real number. Okay, so that is what my c2 is. Okay, so yeah, this is my vector v2. For simplicity, again, again you are understanding that this is some vector in the like I cap, right? So this is in this direction. Okay, and this is scaling. Okay, this can take any value between this scaled. Okay, and if I multiply with this vector with the a matrix, then this won't be transformed. Our direction will be this only. Direction will not change. Direction will be this only. Okay, so that is the main crux, right? So for simplicity, let me write this in a better manner. For simplicity, simply take c2 equals to 1. So my v2 vector equals to 0 comma 1. Okay, c2 vector v2 vector equals to 0 comma 1. So yeah, this is one example. So this lecture has already gone long, so in the next lecture I will like take few more examples of special matrices and find the eigenvectors of those matrices, and also we'll understand the properties of eigenvectors and eigenvalues, and like understand few concepts. That from there we'll get the conclusion of why do we need to use this. Okay, so yeah, thank you for watching.